So today I want to go through the anomaly inflow, and I will be extending off what Jesse did last week in his construction of the picture anomaly inflow and understanding how this applies to the particle in a circle. In particular, let me just get some stuff. Um, the idea for this talk, so anomaly inflow part two. First, I want to just review the inflow mechanism, the anomaly inflow. Just a quick recap of things. And then the second part is just mention how this ties into tooth anomalies, in particular RG flows and the anomaly matching conditions. So these are very important, in particular for studying IR, the IR theory of the IR flow of a UV theory. But also generally applies to other deformations of the theory, not just RG, which is a special example of that. So then the final bit will be to understand a particular example, the particle on a circle. So just the quantum mechanics, which we can understand from very well from different perspectives, and we'll be applying the path integral approach to study the anomaly. So previously, a few weeks ago, Jesse showed that the anomaly is associated with projective, trying to turn the linearized space through the vector space into projective space. And then by doing that, you pick up a anomalous term from going from into that transition. And then the final bit, there's just a few technical details which I still don't have a full grasp on, and perhaps we would be useful to discuss them together. But I'll go through the bits that are clear at the moment. Okay, so the idea first you want to start with is, you might have a theory S, and it's got a particular symmetry group. So action S, and then it's got a particular symmetry group G. And these things may be global or there may be there may be local symmetries or global symmetries. But we can study the anomalies of the global symmetries. This isn't to say that these anomalies prohibit the theory from being realized. It just means that we can't gauge a symmetry, and instead these provide a nice way to measure certain properties of the theory. Um, so in particular, what we want to do is suppose we have our theory, our action, which may be defined as some sort of, we can upgrade it to be, so suppose we do have a global symmetry. Then the idea is we want to upgrade it to be a gauge symmetry. So we then take our theory, which is defined on some space X, and we associate with it. So this is just like, say, the manifold in which the theory is normally defined on, and then we associate it with it some sort of like principal bundle, where then we associate G now to be a gauge group. So by doing this, what we do is we basically have, we insert a background gauge field into the theory. So for example, you might just have, the normal Lagrangian for charge scalar field, which has a U1, phi goes to e to the I alpha phi. And then what we do is we upgrade this to a gauge field, gauge theory, by just replacing these, of course, with covariant derivatives and so forth. This can be plus I G a mu and so forth. Um, where now these are going to be gauge theories. So this is the general construction we do. Even if it is a global symmetry, then we can upgrade it to be a gauge symmetry. So with any gauge symmetry, we have the potential idea of it having being anomalous. So in essence, in this construction, um, the total symmetry group, so we might have, say, G and H, where G will be some gauge symmetry, and then H will be some residual global symmetry. And then I'm just mentioning this because this will be important to understand the type of, say, anomalies that we can have. So we can basically classify our anomalies in the following way. So let me move this over here. Oops. Cool. So we can have different symmetry types. And I'm just going to say this is for G. So G, before we do the construction, it can be, before we upgrade it to a gauge field, it can either be a gauge field originally. So it can either be a gauge symmetry or it could be a global symmetry as an example I just gave. Then we have two options for once we do this, the transformations we can do. We can either do a gauge transformation by G, or we could do something which we would call like a mixed transformation. So this would be by the global symmetry H. And when we do this, we get, in the case of picking up an anomaly term from the gauge transformation, this is bad because it means we have something pathological going on. There is an asterisk here, but we will talk a bit about this later. And then for the global ones, right, let's, for the mixed one, then we have, as for the example of the ABJ, this means that we uh, break H to a potentially discrete, but it means that the entire group cannot survive, but a subset must. In the case of global ones, there's nothing wrong with this because we never assumed anything about it being gauged to begin with, but instead we have what we call a Tuft anomaly. And then these sort of things will allow us to classify certain topological features of the theory. In particular, for this asterisk, there's two cases. The first one we will discuss, which will be anomaly inflow. And then the second one is something called anomaly-matching conditions. What I mean by this particular one is, as example, in the standard model, where if you were just to consider, say, an electron by itself, that's going to be anomalous under the gauge theory of the standard model. But if you consider all of the leptons, then all the anomalies perfectly cancel out and so forth. But yes. Okay. So in general, since we're considering these on, we can, as we have a background gauge field, we can write our partition function with this background gauge field parameter A, which we won't necessarily specify. But then we can make the following anomaly ansatz. So this is the case ansatz. For example, this is seen in the chiral anomalies and some other variations as well. But in general, this is a nice picture which we can pick up. Under a transformation, we will say So this could be the G transformation, or it could be the uh, global H transformation, etc. This will turn into a lambda, where we're just saying lambda is the parameter of the transformation. And then the ansatz is going to be, it's going to be the original petition function. Yes, so let me just notate this as partition function. And it's going to be multiplied by the anomaly term, where X is our space-time manifold. Not this one, A. So here lambda is the parameter of the transformation, and then A is going to be our background gauge fields. So if this was to be a real gauge field with a real gauge transform a gauge field, then this exponential term wouldn't be allowed because we want the theory to be gauged. So therefore, these things shouldn't be detectable or have any impact on the theory. But there is a slight caveat, which Jesse mentioned before, is something which we can call the anomaly cohomology. I don't understand the technical details of this, but I'll just give a schematic outline, and then hopefully, maybe in future weeks, we could discuss a bit more details. I tried thinking about how this relates to the particle in a circle example, but uh, it's tricky. I wasn't able to work through those details, but maybe we can discuss about it later. So the idea is that you can, for example, under, e.g. under regularization, you have different regularization schemes. Uh, you add counter terms to your action. Counter terms to the action, and then this results in implies the petition function is subject to a regularization scheme ambiguity. In particular, it should be that ZA is going to be, should be equivalent to ZA exponential of 2 pi I x beta A, where here beta A corresponds to our counter terms that we add to the theory. Okay, so in particular, what this means is then under a gauge transformation, so not under a gauge transformation, but under the symmetry transformation, whether it be the global one or the gauge one, then this thing will be equal to the original one. Let me just write this out in full very quickly. X alpha. So this is what we had before, and then it's going to be equal to this, but then we can also add in, will be equivalent to this one plus the scheme term. So in essence, what this says is that alpha is going to be equivalent. So our anomaly field alpha will be equivalent to alpha plus beta. So in particular, this defines a cohomology. For what I've seen briefly in one of the literature, in part of the literature, is this is sort of a differential cohomology. It's either topological cohomology or differential cohomology. There's some subtle details which I don't fully understand, but
I think
in
it should
essence,
be
you have the equivalent.
delta
Yeah.
delta beta. I think it should be
Um,
delta beta.
yeah, I don't understand what that means, but
So I think all it's saying is you want to consider anomalies that can't be redefined away or reabsorbed into counter terms. So your beta
hmm,
is something arising from your choice of counter terms, and maybe it looks naively like you have an anomaly, but actually you can absorb it into a counter term. So then what we really want to consider are anomalies that are inequivalent that you can't transform into one another by adding counter terms. So I think as well
sure.
in the line above, it should also be a delta beta as well, right? Because it's
So
saying
you're
when
saying
you,
that's different to this beta? Yeah.
no, so I think that beta is supposed to um, include some combination of counter terms. It's meant to represent the counter terms. So then
Yeah.
when you vary the um, when you perform the transformation, right, your path integral
Hmm.
transforms um, to pick up this alpha term. But
Yeah.
then it also, I think, uh, because beta should transform as well, so it picks up some variation of beta. So your original
Okay.
thing
Okay,
transforms
I
by a
see.
total thing, alpha plus
Hmm.
delta beta, whatever the variation of beta is.
Okay, I see. So beta, the idea is that beta under this variation
Yeah,
will be beta alpha plus delta
yeah, exactly.
beta alpha A, where then
Yeah,
the delta is appropriate to that. Okay, so that,
yeah,
that makes
yeah,
more
yeah, yeah.
sense.
So I
Yeah,
don't think
thanks for
it's
that,
like
Jesse.
super, it's not meant to be super crazy, I think. I think yeah, it's just a technical note that says, yeah, sometimes maybe it looks like you have an anomaly, but it's not actually because you have some ambiguity in your choice of counter terms and you can
Hmm.
absorb it.
Yeah, so then you're going to pick up here. Um, what was it writing? Oh, minus 2 pi I x delta beta. So that's the variation of A. Yes. And then this one goes away. Um, cool. And then we can also consider this is going to be equivalent to just the transformation without the beta term. So basically, let's call this one. This is going to be the right-hand side, and then this one is the transformation of the left-hand side will be just this. Yep. So then these are going to define a cohomology where the equivalence classes are going to be the total set of anomalies, mod out all of the uh, equivalent relations. So in particular, the bit that I don't quite understand, but they say that this defines a discrete cohomology. So the cohomology is discrete. And in particular, what is useful about this is this means that the anomaly equivalence class is going to be invariant under continuous deformations of the original theory. The theory, yes. And for example, some ways you can do this is by smoothly varying the Lagrangian parameters. Another way is by adding infinitely massive, well, asymptotically infinitely massive fields. And then the classic one is just, of course, RG flow, renormalization group flow, where you continuously vary the Lagrangian parameters and then the fields become massive. The massive fields drop out. they become infinitely massive in that context. Okay, so in principle, importantly, it means that these equivalence classes are going to be um, invariant under, so these alphas are going to be invariant under RG flow. And so this leads to something known as anomaly matching, which basically says that the IR theory of so the alpha of the IR has to be the same thing as the anomaly equivalence class of the UV, which is really nice because then at different stages along our RG flow, we are able to say, so at these different energy scales, we're able to say quantitative things about the theories and how to relate, even if we can't necessarily compute the explicit deformations of the theories. So then just a quick thing to mention about how this, uh, what Jesse said last week is in anomaly inflow mechanism. So there's really like two purposes for this. One way, which is how it appears, for example, in condensed matter physics, is just a way to counterbalance gauge anomalies on the boundary. For example, in the quantum Hall effect, where you have a topological theory in the bulk. And then the second way, which is what we're really interested in, is it provides a nice way to measure 't anomalies of our theories. So the general idea is that you have a theory X, a theory S, um, defined on the manifold X. And then what we want to do is we want to extend it to a manifold Y, where the boundary of Y is going to be our original field X. So basically we extend the Lagrangian to be a Lagrangian defined over Y, where of course we want them to match. So then at X, which is the boundary, it's just going to be original Lagrangian. And then we want our fields, we want to extend these, maybe not these map arrows, these ones. We want to extend this to this. So then, of course, and so forth. So the general idea is that, say, you have a boundary X, and then you have the innards Y or the bulk Y, and so forth. Um, yeah, so you can picture this, say, like as a quantum Hall effect, which is a nice condensed matter physical example. In the original context, it was defined for four-dimensional fermions and seeing how to relate to a five-dimensional um, bulk theory. It's hard to necessarily say if this is physical, but these sort of mechanisms are very useful. So the mathematics seems to work. So we just work with it, even if there are like ontological issues with such things. If they were, you know, if you were to analyze things using a five-dimensional theory, even if, space-time is only four dimensions and so forth. But we just work with it, and then we can ask those questions about those more philosophical questions later if need be. But for this analysis, we don't really care about it. Um, so what we want for this bulk Lagrangian in particular is, sorry, the bulk one. Um, I I should correct this. We don't actually want to extend the Lagrangian. That's not what we want to do. We only want to extend these background gauge fields into the bulk. And instead, we want to construct a new bulk Lagrangian omega defined on A. And in particular, we construct something which we call an invertible field theory. So these have no dynamical fields. It's just going to, which is why we call it invertible, because we can just literally invert this exponential, and it's going to be 2 pi I y omega alpha. So this is kind of what we want. This is like the goal. Um, want to construct, or we want to have this. And so this is the first property. One, we want to construct. And two, we want transforms as it just picks up the anomaly term to balance out the original one. So then the really nice property is that we're able to define a, this implies we can define a modified partition function, Z tilde, on our background fields, which will be the original partition function multiplied by this bulk partition function. And uh, the wonderful thing, of course, is then this means that under these transformations, it's going to be invariant. It's not going to pick up any anomaly terms. They're all going to cancel out, which is going to be really nice. So then it means our combined bulk plus boundary system will be anomaly free. So for example, you may have an anomalous theory. Let's not do that one. You may have anomalous theory on the boundary of your on the boundary X, and also maybe anomalous inside the bulk, but then the two cancel out to give a anomaly-free theory, which is nice. Cool. So okay, so this means that this is going to be anomaly-free. Might just make this green because why not? Um, yeah, so one of the important implications I mentioned before is the anomaly cohomology is anomaly, oops, that's not how you spell anomaly. Anomaly matching conditions. Well, let's just call it anomaly matching. So the idea is that, so this is basically, this is really all an implication of um, the anomaly cohomology. Anomaly cohomology. And in particular, we can consider, so we wanted this smooth deformations. And in the picture of the anomaly inflow, we can consider smooth deformations under where our original, so our bulk invertible field theory is then smoothly deformed to omega lambda. And we call all of these Lagrangians, we can define an equivalence class, uh, omega lambda. So these are going to be our equivalence classes. Of the theory. And of course, this is going to be an invariant under um, continuous variations, as I said before, and then RG flow, and then of course, etc. Yeah. So then our original anomalous theory, so we can also then vary, let's write it like this. Our original theory will also transform like this. Oh, I should also, perhaps let me put this as mu, so we can distinguish between the symmetry transformations and the So let lambda be these symmetry transformations, and then you can be the deformation transformations. But like in the notes that we're working through, they just write lambda for both. So that could potentially be a bit confusing, but it should be cleared from context. So then this theory is going to be characterized because we have the equivalence of the anomaly inflow condition. This is going to be characterized by our deformation classes, um, omega mu. So the important claim here, which allows us to classify the IR physics, is that if the equivalence class is non-zero, then Z mu um, along all of mu will be not invertible. So in other words, what this means is it's not going to be a trivial theory. So this means it basically is like a non-trivial theory. So to unpack this, what this really means is that, for example, so let's say as an example, if you take RG flow and you go from the UV, which could be mu is zero, and then to the IR, which could be mu is going to be infinity, then you're going to have, let's write it like this. U lambda non-zero implies one of two conditions. It's going to be either gapless and it's going to have be gapless with a non-trivial spectrum. So it's going to have massless interacting CFT, or it's going to be gapped, but it's going to have a non-trivial topological quantum field theory. Okay. So this is really good because basically what we started with is we had our symmetry group, let's say G cross H. And this was going to be, let's say in this context, this was purely a global symmetries. But then what we've done is we've gauged G. And then what we can see is that if this is non-zero, we immediately know that we can identify, we can say something about the spectrum. I'm just going to write, say, no something. No, no, we know in particular, let me rewrite this. We know that the spectrum of the theory is non-zero, a non-trivial along RG flow, which is a very powerful statement. So this is one of the key important properties of 't Hooft anomalies. I'm not familiar with if there's any other important implications of 't Hooft anomalies, but these are the key ones that basically these have to match. So if we had, say, a theory, I'm just going to write this as, if we had one theory, say it had, let's say we have two theories. So we have mu lambda 1 and then mu lambda, um, sorry, omega mu 1 and omega mu 2. And then this is going to have, say, deformation class mu 1. And then this is going to have deformation class mu 2. If they're not equal, then this would imply that we can't, there is no way to deform one theory into the other, which is a really, really important statement. Okay, so now we've done that. Now we can move on to the particular example of particle in a circle. Um,
Maybe
so
could
that
I
took me
just
a
make
little
a
bit,
quick comment?
yeah? Yeah,
So
sure.
like this, if you scroll up a little,
Mm-hmm.
this idea of looking at the IR theory,
Yeah.
it's really quite powerful because in general, if you give a random quantum field theory, for example, the IR generically will be completely trivial, right? If you think about the sort of theories you're familiar with, if you
Mm.
have massive particles or something, once you flow down to below the particle mass, um, there's just no excitations. You have a trivial field theory. And really, the only times that we don't have a completely trivial uh, not ground state, but a completely trivial IR is there's really only like a few mechanisms that we know of. So, for example, you could have these gapless states, um, and really the only known mechanisms for this are things like spontaneous symmetry breaking. So if
Yeah.
you remember, you think, oh, maybe we have like the photon or something. But we talked before, this actually comes from a broken symmetry. So the only times we get these um, these gapless these gapless IR is through something like SSB. Um, if we have fermions, we can have Fermi surfaces.
Hmm.
And you can have like quantum criticality effects where you can tune parameters to very, very specific values, so that for a very particular set of values, you get uh, a gapless um, a gapless IR. So in general, like, these things are quite rare. So it's very nice to have
Mm.
like this tool um, that can tell you that you have a non-trivial IR.
Yeah. And this sort of stuff is very important, say for quantum computation, right? Because you want to have these non-trivial topological field theories which you can control.
Yeah, exactly.
Yeah.
Yeah. So even in a gap theory, like normally if your theory is gapped, you just have a single trivial ground state. So again, like we talked about in these TQFTs, you can actually have degenerate ground states, which is quite a special feature.
Yeah. Yeah. Yeah.
Sorry for
Um,
interrupting.
no, no, it's good. It's good. It's good to make the comments. Like, please, anyone, please feel free to interrupt if there's any questions or like any like further comments that you want to make that I haven't addressed. Because I mean, I'm still trying to learn this stuff. But um, yeah, actually, before I go on, this one small caveat is that, you know, there's a ca um, there's one exception. There's one exception to this. It could just be that like the symmetry group is spontaneously broken. Uh, which then, I mean, that's going to then give you some gold zone modes. But yeah, that's the one exception which you would have to really, sorry, that's the one exception to the whole picture because basically, like in this assumption, we have assumed, so the key assumption to above is that the G cross H symmetry group is going to be preserved along the flow mu because then if it's not, then I can't say if the Jesse, do you know if the IR would could be trivial? Could the IR be trivial if the symmetry group is spontaneously broken? My intuition says it's going to be non-trivial, but it's going to have Goldstone modes at
I mean,
least.
yeah,
It's
if you get a
yeah,
massless Goldstone mode, then it's gapless.
it's yeah. It's going to contain. Oh, true. It's going to contain. Uh, good point. Goldstone modes, which implies non-trivial gapless to above analysis. Yeah. Okay. So in the remaining time, I'm going to do the particle in a circle. If anyone has to go, please try to stay because it is a good example to go through, which should hopefully clarify some of the theoretical pictures above. But I will upload my notes as well, so you can always read through these if you need to go early. So as before, the idea is we have our circle. Uh, it's not a circle, but I'll just actually let me fix this up. So we have our circle and we have our charge bead, and the charge bead is going to move around the circle. And in particular, it's got to have some sort of periodicity, which is going to be after some time tau, or capital T, it's then going to be equal to the initial point. So this is the period mod 2 pi. So in general, this will be x0 plus 2 pi n for n some integer, right? And this is just going to classify the winding number, the theory. So we have our classical Lagrangian. L is going to be half x dot squared plus theta on 2 pi x dot. So the first term is just going to be the general kinetic. So this is like a kinetic term. And this second theta term is going to be, say, from like a magnetic field. And as we mentioned before, there are two symmetries. Let me go a new page. There's going to be two symmetries. The first one is going to be the shift symmetry, which is going to then be x is going to go to minus lambda for some parameter lambda. And then the reflection, or you could imagine like a charge conjugation, x is going to go to minus x. So the idea is we want to study the 't Hooft anomaly of U lambda. So the nice thing about this is because this is a continuous symmetry group, this is going to be basically like, this is like a U1 symmetry. And then this is going to be um, it's not technically U1, but it's SO2 anyway. Um, where is it? Yeah. And then this one is going to be Z2. So you have those two. So the nice thing about the U lambda symmetry is that since it's a continuous group, we can do the construction above where we put this on a normal principal bundle, and then we can, um, basically upgrade this to be a gauge symmetry. So if we do that, then we can make this be a gauge sim, and then we can write our new Lagrangian. L is going to be x dot plus a mu. So this is sort of like a covariant derivatives, where then we have the transformation of the gauge field is going to be a mu is going to be a mu plus d lambda dt, where then t, I should mention before, is the time variable. Okay, so now we can upgrade this to be the quantum theory, where we can put this on in our partition function. It's going to be e to the I integral dt of L. Okay, so just to clarify, make the analysis a bit simpler, we then want to Wick rotate. So I'm just going to replace t with tau. And the second thing is we can also add our counter terms, add the counter term. So this was like our beta, like the beta term we had before. So then we have z equals z dx e to the minus. I'm going to just put 0 here to make it distinguish. And I just want to call the new thing L. So it'd be d tau L, where we have L is going to be equal to half x dot plus a mu squared minus I on this one. Okay, plus, and then this is going to be our counter term. So this is the counter term. Okay, so a couple immediate consequences of this is that in order for this to be consistent, we need that theta is equivalent to theta plus 2 pi. Oh, also these are constants, so I should say here we're assuming that theta is a constant. The second thing, so this means that theta is going to be like a genuine angle. The second thing is that k has to be quantized. So they're going to particularly take integer values. Um, and the reason why this is the case is because there's an additional thing we want to do is we want to compactify the domain. So then we replace it from being an integral dtl, unspecified integration bounds. We want to make this be periodic. So we'll make that dtau. So it's going to go from, say, 0 to uh, to capital T or something like that, which was going to be our, say, original one. Yep. And then for simplicity, I'm just going to say that x of t is going to be probably x0 plus 2 pi. So it just has like a winding number of 1. So this will be like a genuine period. Okay. Okay, so I'll just quickly check this. So for example, if we do um, the second term, it's going to be I theta on 2 pi. And then let's say, um, I'm just going to shift it to be, let's write it like this. Minus I on 2 pi integral theta plus delta theta. Let's make it phi just to less numbers. X dot, which then will be e to the I 2 pi theta plus phi, and then we integrate, and then we basically have x of tau minus x of t minus x of 0, which then we said is going to be equal to 2 pi, which is then going to be minus I theta plus pi, which implies that we need pi to be 2 pi. So there we go. So we have that it's going to be periodic like this. Okay, so let me do this as 1, 2, and then this is proof of 1. And then let me just show the second one. Okay, so we were integrating this term here. So we have e to the I, did I do plus? Yeah. Ik, so these are going to be integers we can bring out, a. And the idea is we want to then do our gauge transformation. And this is then going to be AK plus IK lambda dot, which then will be, so this is the gauge transformation where A goes to A plus lambda dot. And then this is going to be, let me just quickly evaluate this. This thing, as before, will be lambda t minus lambda 0. And then we just want to claim this is going to be 2 pi, so it's going to have the periodic boundary conditions as well. And then, so we have e to the ik ua, e to the ik 2 pi. So for this to work, this means that k must be an integer. So there we go. So we got that as well. So that's just a few things just to check. Okay, so now we want to say is what happens under C. So far all we've done is just considered the um check the consistency conditions of the other fields. Oh, I should also mention before we do that is just that the final thing to mention is that L is gauge invariant. Um, as we just saw, if you have the quantum theory, then the topological term will be invariant. But then you also have that the um, obviously x plus a will just go to x minus lambda dot plus x plus lambda dot, which is just x dot plus a. So that's going to be, that's good. And then we had that. So the first one, this one. And then the second thing, obviously, was that k. A was then going to be equivalent to like just ka under the plus ka, sorry, k lambda dot, as we just showed above, because we have k quantized, since k is an integer. So that's nice. Okay, so now we want to check what happens to our function under C. So we don't actually, when we consider these anomaly terms for the 't ones, this is why I was mentioning about the mixed anomalies before. We're not considering under what happens. So this is going to be sort of like a mixed 't anomaly. So we don't actually care about what happens to the transformation of the gauge field under the gauge transformation because we've seen that everything is okay. We want to see what happens to the gauge field under the C transformation. So this was equivalent as we saw in Jesse's talk 2 weeks ago, using with the projective representations, the violation you get when you conjugate, rotate, then conjugate again is not the same thing as just the rotation because you pick up the extra term from the projective representation associated with projective representations. Okay. So you get a tooth anomaly, which we'll just see. Okay, so what we want is, remember, under C, x will go to minus x, but then we also want that a will just go to minus a. Okay, so the important thing is we need to check different angles. So I'm just going to leave it as a various angle. But in particular, remember these things are only going to be well defined for when theta is 0. So it's only going to be a symmetry. So this is a symmetry if theta is 0 or theta is going to be pi. But let's just do it under a general transformation. So in particular, we have x dot plus a will go to um, minus x dot minus a. So then we have this entire term. Let me just rewrite this up properly. Okay. So then our Lagrangian will vary. Let me just copy paste this one and then I'll just fill in the terms. So where was it? I was here. Okay. So let me delete. Let's call this one LC. And then LC, so this is under C. This one here was going to be minus x dot minus a, but then you square it, so you just get the same thing back. So that's nice. The second one, again, now we pick up a plus, and then the third one, we get a minus sign here. So we can compensate for these terms. In particular, if we, let me write it like this. Um, so just to balance these things out, then you can rewrite the previous ones. So you just put it back in as if nothing happened. Um, plus, then this is going to be plus I theta on pi x dot plus, uh, oh, sorry, minus. This one's minus. Oh, no, this one is plus, sorry. And this is going to be plus I theta on pi a minus 2ik a. So then we have the original Lagrangian plus two lots of the I theta on 2 pi x term plus I times 2 pi on 2 theta minus 2k. In particular, I'm going to move. No, that's fine. Just leave it like this. A. I'm actually going to slightly adjust things a little bit. Let me just quickly do. Actually, yeah, let me just do this. Let's make this a minus counter term, so then we can make everything positive. Um, yeah, let's leave this. That's okay. That's fine. So we just need to make this plus. So that's going to be plus. Oh, no, this one, sorry. This will be minus. Give me a sec, sorry. Um, oh, no, that's fine. Okay. Mm, wait a second. Um, yeah, let me actually just quickly trace this properly. So this is going to then be, that's fine. So then this is going to be 2. We want the minus. Um, yeah, let's make this one plus here. And if I make this one plus, then this thing must be that one's plus there, so then this one's minus. So then, yeah, okay, so that's fine. I put a minus sign there already, so that's okay. Okay, cool. So this is going to be a plus term. Let me fix this up. Okay, so in particular, then we want to consider this e to the integral d tau L will then shift to e to the minus integral L e to the minus 2I theta on 2 pi integral x dot. And then this is the anomaly term here. So this is going to be importantly the anomaly one. It's going to be minus I 2 pi on 2 theta, sorry, 2 theta on 2 pi plus, let me move these around so it's consistent with the notes, 2k plus 2 theta on 2 pi integral d tau a. Sorry, I missed one of these. Okay, so this is then going to be our anomaly thing, if you remember before, which was going to be minus, sorry, it was minus 2 pi I integral x, which is what we have, alpha lambda a. So here the lambda is associated with um, the C transformation. So this is going to be associated with the conjugation transformation. Then this, just to quickly do this, this is going to be, as we had before, this is going to be t minus x0, which is going to be 2 pi. So then the e to the minus 2I theta 2 pi term will be e to the minus 2I theta. So this thing is going to be a symmetry 1. This will be a symmetry 1 if, of course, theta is going to be equal to 0 or pi, which is what we claimed before in the classical theory. But, so this means this one is going to be the symmetry. But as I said before, but we have the anomalous phase. Which is e to the minus I 2k plus 1. Sorry, let me write this. Plus 2 around 2 pi. dt tau a. Okay, so we have this anomalous phase. So we have two different conditions that we need to. Okay, so let me write this properly. So if theta equals 0 or pi, then ZA will transform as ZAC, which will be the original ZA times by the exponential of minus I 2k plus 2 theta on 2 pi by this term here. Okay. So this is, as I said, the anomaly term. So we have two different cases we want to consider. So the first one is theta is 0, in which case we have 2k plus 2 pi on 2 theta is going to be equal to 2k, which is going to be which we can write as let me write this properly, which can be absorbed into our counter terms. And then, so that's okay. So we don't have anything of the sort. Oh, sorry. Sorry, let me say that again. So if theta is 0, then this is going to be that. So this means invariant, which implies this is going to be invariant if k is 0. So we want k to be 0 as our choice. So that's nice. We can do that. Whereas if theta is going to be pi, we're in trouble because then we have 2k plus 2 theta on 2 pi is going to, of course, be 2k plus 1, which implies this thing is going to be invariant if k is equal to minus a half. But that's bad. As I just said before, in order for this to be gauge invariant, it has to be k an integer. So there's the issue. So this is why we call this the theta equals pi phase an anomalous phase. So gauge invariance requires k in z. Okay, so that's an abstraction. But this is where the anomaly inflow phase comes into play. So what we can do is we can originally we have, so this is where we make the connection to anomaly inflow. So we have our S1, which was going to be the theory on the compactified theory. And then we want to suppose there exists some it's the boundary of some theory Y. So for example, you could just imagine a disk, so a circle with a disk in it. And then we want to extend our gauge fields before again, we want to extend them to be a tilde. So this is going to be on y. And the nice thing about this is now we're able to construct a connection. Sorry, no connection, a curvature. So we can write the curvature as dA, where just want to be careful. I'm going to include the the one form. So make this one form because A before was not it was just a constant. So now this makes it F is a valid two form. Okay. So then we can construct our topological theory to be, it's just going to be the exponential of, in the notes say they have this, but we can derive it explicitly. And then this thing is going to balance out the anomaly from there's particle in the circle term. Let's see how we do this. So just to write this example, so we have exponential of minus, right, like this, minus 2k plus 1 I. Did I put I? I think I missed it. No, I is there. And then we have, this is integral on the circle of our field A d tau. And then this thing here is then going to be equal to the boundary on y a d tau, which then by Stokes' theorem, it's just going to be y d of a d tau, which is then going to be y f. So there we go. So we have then this thing here is going to be exponential of minus 2k plus 1 I integral y f. Okay, so that's nice. So then we want the combined theory to be equal to the original one plus our new exponential 2 pi I integral y omega f, where f is omega f is going to be omega a. Let me write that. Where then omega is going to be the non-invertible, the invertible field theory. Yeah, so under this transform, so this is going to be, so here we want omega a is going to be some unknown coefficient times by f. Let me just call, uh, what's a nice letter? Let me think. Kappa. Let's just say kappa. Kappa f. Okay, so when we do this, the nice thing is under these gauge transformations, then we have f, sorry, not gauge transformation, I misspoke. Because we're applying C, that means f will transform into negative f. That's pretty straightforward to check. So therefore we have ZA of C. So now we're gonna, so let me write this here. Under the anomalous, anomalous C transformation, this is then going to be equal to ZAC. Oh, of course, these are extended. I'm going to just put arrows on here to make it clear that these are extended. So this is well defined. Okay, so then this is going to be equal to this times exponential of 2 pi I gamma kappa minus f. And then as we saw before, this z is then going to be equal to ZA exponential of, where was it? It was going to be minus I 2k plus 1. And then by Stokes' theorem, this is equivalent to just the integral over f, and exponential 2 pi I gamma y let me move this here. So this is going to be minus 2 pi I gamma y f, which then, in order this to be anomaly free, we require this then to be equal to just 2 pi I gamma kappa f. So from this necessarily means uh, this means that, give me a sec, this is going to be 2k plus 1 plus 1 is going to be equal to minus kappa. Sorry, 2 kappa. I missed a kappa. Oh, I see. In here. So it's kappa. Kappa. So then we have kappa is then going to be minus a half of 2k plus 1. So then we have that our total what theory. Sorry, these are going to be like this. Will be equal to z of a times by the exponential of um, minus I on 2k plus 1, and then the integral of the curvature term. Let me just check this makes sense. Yeah, I'm just going to leave it with this for now, but is there any further questions? Uh, yeah, does no one have any questions at the moment?
I mean, maybe I can comment and say that, like, this circle example may seem a bit artificial, but it's actually like a quite nice toy model for looking at stuff like a parity anomaly or something. You get the same sort of thing with this K, where it has to be a half integer if you
Hmm.
want to get rid of the anomaly. So you need to add something that's like a Chern-Simons term in the quantum theory, but with a half integer, um, which you can't have because it's supposed to be integer quantized. So it's actually a quite nice toy model for that.
Yeah, yeah. We can also consider it if it's going to be discrete gauge field, but I was trying to play around with that, but I couldn't figure out quite how to do it because it requires quite a bit of, say, algebraic topology, which I'm not entirely on top of. Perhaps it might be worthwhile to just share, particularly parts of the nodes. Let me just do this. So I'll stop sharing this. Stop this one. And then let me share another one. Yeah. Okay. So in particular, then they say you can also, instead of considering the full, um, continuous symmetry group, so the gauge group. So what we identified before, this sort of thing is like identifying the 't Hooft anomalies. And then in principle, that should help you understand how the model changes under continuous variations. Um, but then you can also consider it just for a finite group, where then because we have this discrete group, we have zero curvature. And then because we have zero curvature, it means that we can define a cohomology on the manifold without the symmetry group. And then, this is the discrete group. And then in principle, you should still be able to do the same construction, even though the method, say, like I just described before, the particular example assumes you have a continuous symmetry group because you have the standard principal bundles. Um, it's in principle, it seems you can do it, but I'm not clear how to do it. I haven't studied enough algebraic topology to do it. They also have a good example with the um, T invariant fermion theory, which you can when you work through, you also get a similar construction. They don't write down a particular invertible field theory that you would have to get, but you have a similar construction you can do as well. Um, yeah, that's pretty much it from relevant for this. If Does anyone have any further questions about the material so far? If not, then I will just end it here.